Thank you, Paul. What a fun thing to remember. You know, first title that I thought of was, Marcello was going to talk about information theory in an industrial lab. So I said, well, I'm going to talk about communications theory in an industrial lab. But then I recall that actually Jack Wolf told me that Bell Labs is the most academic place that he has ever been. So I said, really, this would be disingenuous to call this industrial lab. How many people know what this is? Frank, I knew you would. Yes. So this is the antenna, which was used by later Nobel Prize winners Arno Penzias and Wilson. And they heard background radiation, actually, because they had a big enough antenna. They didn't know what were they going to hear. They didn't actually building this antenna to hear that. They built it for other reasons. They thought it was noise. There is a very, very long story. Someone at Princeton was trying to, actually, who was a real scientist, trying to actually build an antenna to hear background radiations. So many things happened by luck. I didn't know really whether to believe this to Jack until I started seeing pictures like this, very sunny. You know, and if you look at there, then there is these two cool-looking people, Paul and Jack here. What you see, of course, first is the students. And then I believed him because while they were there being cool, look at these two guys, Paul and Jack, we were doing real work at Bell Labs. So I'm sorry, Paul, only the closest friends I represented as cartoons in this talk. So what I'm going to say is, while you're keeping your fingers crossed, because many things depend on luck, there may be some things to also keep in mind. And so I'll tell you about 3 traps to avoid, 4 rules to question, some advice to consider, and 2 bosses you would be lucky to have to hear you out. OK, so what are the traps to avoid? This is a picture of Cambridge, actually of Newton's apple here. And in 2010, there was a conference, or actually a special half a year, on stochastic models in information theory. And there was a very nice workshop, which I attended for a week. And then afterwards, just when everyone left, I was going to leave a few days later. There was this sliding volcano erupted, and I was trapped there. So I had to talk with people. And I asked them, so what are you doing? They were mathematicians, and they told me about really interesting math models. And there were these large graphs and something which seemed like percolation. And they asked, what are you doing? What is this for? They said, well, it's communications networks. And I said, well, but you know, my department at Bell Labs is called Mathematics of Communications and Networks, so maybe this is sensor networks from what they were describing. They said, no, it's communications networks. I said, wow, maybe it's social networks. I said, no, it's communications networks. I said, I really didn't know these communications networks, so I was getting a little bit desperate, so I said, well, maybe it's the butterfly. They said, not really, you know, it's a large graph and everything. I got really completely desperate. I was starting to see butterflies myself. And then it hit me that actually they had these models from the 60s that their advisors worked on. And there were some phone networks and phone networking issues that they were trying to address. So what one should really ask himself is, are you working on networks from your advisor's dissertation? And interesting thing is that with very little math, they really could have addressed these modern things that people are now interested to find things out. It's easy to get caught in the past, but there is a person who would never get caught. Here is Neil Sloan, my colleague from Bell Labs. And his last talk, actually, at Bell Labs when he moved to Shannon Labs, 15 minutes away from Bell Labs, was about Grassmannian manifolds. And he said that he actually started thinking about that when someone asked him, a friend asked him, how to intersect radiation beams, or how to position them in a 3-dimensional space so that they intersect at a tumor, but they're very far away from each other at a healthy tissue. And And what Neil did is solve that problem and then said, okay, let's now consider m-dimensional laser beams or manifolds and pack them in m-dimensional spaces. And what he didn't do is claim that he was working on n-dimensional tumors. And that is what made difference for him. What he did is learned many other things, from oil olive classification in Italy to quantum error correction, and actually found applications for what he was doing. But what people usually do in these situations, they really start working on 6-dimensional beams for 10-dimensional tumors, and then they're not listened to. All right. So third trap, and the last I'm going to mention, is generating a dense sense of scenarios. Whatever we do, we sort of want to cover every single possibility. And tomorrow in practice, actually what will happen is, even if you worked on 1,000 different scenarios, there will be the 1,001st that you didn't address, and exactly that one will be something that people care about. So what I'm saying here, try not to be finding a secrecy capacity when Eve is blonde and sitting on a cornflake, unless you're as famous as the Beatles, and in that case, everyone will think that that has some meaning. So now, what is this? 4 rules to question. Okay. So rule number 1 that people want to say, applied mathematics is applicable and pure is not. And that actually is not true. In fact, I was a little bit interviewing my colleagues at Bell Labs, and I asked Adrian Weingarten, who is a very practical guy, what he thought was practical or applicable. And he said, well, really, I don't know, but be sure to tell them that sometimes fundamental math, pure math, is actually more relevant. And if somebody like him tells that, then it must be somehow true. And we always think applied mathematics is something that you're digging and doing, but it actually matters what you build, not how much you were digging. And pure math will sometimes help you build something better than the applied. Another is a rule is what you learned at school doesn't matter. So let me tell you about something that I did, which actually then I published at that SPIE conference, and that's actually what Paul thought that was the time when we met. We met 2 years before that, but that is what he remembered. And it was only the school knowledge that actually brought me to that conference. So our magnetic recording guys were trying to squeeze more bits on a disk. So what you do, it's very similar to today's, let's say, compute and forward approach. So what you do, you take, if the disks if the bits are close to each other or tiny, you sort of equalize them. You can think about that as a lattice point. It's actually a polynomial. We had a one-dimensional case. And if they're even closer, you have another polynomial. And depending on how close you are, you choose your polynomial. It turned out that when you have actually a head which is on track, that's the best thing to do, to equalize it to something which is closer to what it really is, but has integer coefficients. Now, when you start picking up magnetization from adjacent tracks, what happens is some of these polynomials behave better than the other. And that would be like if in compute and forward I told you equalize that to some faraway point, and it was non-intuitive. So the only thing I could do is go back to the first principles, derive something from school that I knew, and it turned out actually that why this was happening, and people were thinking that they were observing wrong things in the simulation, it turned out that this was happening for the reason of the following reason. Like, if you are making an error in decoding on an intersymbol interference channel, you're actually likely to confuse a sequence which is in the Euclidean norm, the closest one to the one you recorded at the output of the channel. And this is a L2 distance. If you have something recorded on the side track, what hurts you is not the L2 norm, but L1. And there is no way, unless you really go back to school and start deriving very simple things, that you come up with that. So that was kind of something I would question. What you learned in school does matter. And many good things can be just derived going back to the first principles. All right, the third role. Engineers, like patients, lie or do not lie. Well, it's not that they lie really, but it's hard for them to describe you a situation which they really want you to solve. So sometimes they don't know it. There will be cases where they intentionally will mislead you, but they're rare, like in Dr. House episodes. It's usually that they really don't know. And there was an incident that Rudy and I, Rudiger Urbanke and Sasha Barg and I were working on a first, in a few, let's say, years was the first talk in optical. And we were told there are few bits, that was in the late 80s, mid to late 80s, 90s, sorry. There are few bits in the sonnet frame that we could spare. And can you put some kind of error protection? And Sasha came up with these really nice tables where he analyzed everything. He found out that I think it was the BCH code where 2 to 12 or something like that was used. 3 error correcting was something that we should use because the redundancy that they allowed us was like 0.1%. And that was this ad hoc design. Rudy and I found how to implement these things efficiently and so on. And it turned out that after we did all that work, they told us, you know, Nortel has a better code. Like, how can that be possible? We are the best coding theorists you can find for the money. And how can Nortel have better code? Which code is that? They said, well, 255 to 39 read Solomon. So, well, you know, that's 7% of the redundancy. You told us to work with 0.1% of the redundancy. But, you know, that's what we have to live with that. Another thing is everyone can think out of the box. And you know, the rule that does not have an exception only proves the rule that every rule has an exception. This is also, can really everyone think out of the box? And isn't that itself, by itself, thinking in the box? And what it says here is there is this boss who says, you get back to that damn cubicle and start thinking out of the box. So this really depends on our lives. There are things, maybe, I'm sure many people would have liked to stay here my talk, at least that's what they said, but you know, they had to go back to teach classes, take care of so much children and whatnot. So, you know, there is lives that we have so that can we really think out of the box. What is some advice to consider? Okay, we are at the box still. So there was this project for optical, video theme. And they tell us we have to do something about video. But what exactly? We don't know, but we have to think out of the box. And you know, there are many things still at the physical layer and communications and the higher layers, but really information theoretic and coding theoretic that can be done. So why would I go actually into someone else's box, like Disney or something, and do some kind of a video games or whatnot? And then over the years, although I did work on many, many things, and really I think can appreciate how much it takes to go somewhere else, you kind of accumulate your little things and things that you know how to do really well. And now, you know, the danger is actually to get into some other box, and instead of being your true self, you become some ridiculous cartoon character who really doesn't know what he's talking about over there. Okay. All right, should you worry about the presentation? Well, it really matters at the end what you are saying, but this particular thing was, I was asked in 2008 to help with optical modems. And they had this, you know, Reed Solomon code 255, 239, I really, you know, had bad memories about. And so they said, now with these few devices, or I don't know what it was, new speeds or something, this code is really not strong enough for us. Should we take some stronger code, and how much does that going to cost us? And they said our competitors are actually saying they're thinking of using 255 to 23 Ritz-Solomon code. So I drew these things, which you'll find, I don't know, in the books by Proakis, what we do at school, right? And I said, well, but what do you want to achieve? They said, well, we still want to keep this 10 to the minus 12 probability of error outside. And so they somehow couldn't read this. We are here, and this new code, there is this graph, until it occurred to me to actually draw for them something that looks like this. And if they wanted to stay in that field with the 255th elements, and they wanted to play with the rate, then this is where they were. And if they decrease the rate, the performance would get better. The SNR would drop. The SNR for which you need the bit, which would give you the bit error rate of 10 to the minus 12, until it starts going up, right? Because there are two things which are opposing each other. One is that your code is becoming better, but another is that your normalized energy per bit is going down. So if you draw something like this, then somehow all of a sudden they became happy. And that led to other conversations. Also, they started trusting me more and so on. All right. So there are two bosses to hear you out, right? So what would be one? How many people have seen a margin call? So it's a movie about, actually covers maybe not even 24 hours, but in 2008 at the crash of the stock market. And Jeremy Irons plays this kind of a boss from hell, but it's actually not. To me, it's a positive character, and I'll tell you why. So there is a technical person there, kind of a cliche, MIT rocket scientist, who is working for this company, financial company, and he finds out that if something happens, then this curve, they will follow this curve, sort of, in so many words. I mean, this movie is an hour long before this happens. And they call for us his boss and his boss's boss, and finally Jeremy Irons arrives with a helicopter on top of the building. And they have this. And he says, speak to me, like speak as you might to a young child or a golden retriever. And then he goes on to add, it wasn't brains that got me here. I assure you of that. And so, so why is that good? Like bosses today kind of, they either don't want to hear you, or if they hear you, they know coding theory better than you, although they never heard it kind of before. And you worked in 20 years in the field. So what he was saying in that movie was the following. He said, he didn't question. He wanted to say, to understand if this happens, this will happen. He did not really question how this person, technical person, arrived from here to there. That was his job. He trusted him. And at least that's my interpretation. And he thought it's not brains that got him there. His only job was to say which of these possibilities on this side will happen. That was his vision. So once when he knows that this happens, he trusts his employee that something, what he computed. So that is what was good about him. There are also other types of bosses. This was Aaron Weiner. He headed our group for 22 years and died in '97. Just before we celebrated 50 years of Shannon in '98, which then Emre Teleter had to take care of. And I started working in '94, and in '96, Aaron told us, there is this guy who approached me and said he had solved the coding problem. And he said, what does it mean? He said, well, he said, for any rate you give him, he'll find you the best code. And sort of saying, this is really funny. Are you really going to listen to him? He said, he looks sincere to me. And then he said, well, will he come to give us a talk or something? He said, no, because he would like to actually patent these, if it's possible. But then how are we going to judge it? So we had to improvise some cryptographic protocol or something to judge this thing. And so I decided to ask him to provide lists of many of these codes, and we would check them. I mean, we would check them. I would check them, and Rudy. And that's really, actually, we were not looking forward to doing that. I was kind of puzzled that Aaron would pay attention to something like that. So Rudy, before he retired to Switzerland, lived in the fair island of Manhattan and had to drive back and forth there. Had a red car, and he went home, and the following day he managed to get stuck ran out of gas in the Holland Tunnel. And the Holland Tunnel is the tunnel that joins Manhattan and New Jersey, with millions of crazy people ready to kill him behind him. Actually, it was not at this occasion, but it really happened. So the port authority got him back very quickly, pulled him out, and he was back with us. Now our friends, here is Sarab Savari and Jelena Kovacevic, they were not really helpful. Alon was too busy with the first ITA was going to take place 10 years after this event, so he was preparing. And of course, there is always an angel, not very helpful always, and that's Emre. And he arrived, he made copies for us of what to do when the trisector comes. And that's, the trisector is a person who claims that he had solved the problem of trisecting an angle with a compass and straight edge. So this guy, I mean, we don't know at the time, didn't know whether this problem is solvable or not. So it was not exactly the trisector, so it didn't help us. So what happened is, at some point, I found a little line in these papers which didn't match. I knew about something better. And so I said that to Aaron and Rudy, and Aaron said, all right, but this is just one code. Let's, maybe the others are good, but I'll contact this person. So he contacted the person, and I was thinking, no, this is going to go forever. But he didn't. This guy got so disappointed that he never told us a word again. He kind of apologized for this one. Maybe he really had solved something big, but he never contacted us again. So Rudy was happy. Alon was back, sort of, and the life was good again. All right. So with all of this, I hope you got some hints what I think is important and what not. What my experience was important, was not. But after all, there is lots of luck. And although we deal with randomness, many people would not like that, because we really like to have kind of a causal life. And because you wouldn't, I decided to invoke higher authorities. And this is Daniel Kahneman. He won a Nobel Prize in economics. And this is a sentence from this book, which I started reading recently. And he says, success is talent plus luck. And we know that. But he goes on to say that the great success is a little more talent and a lot of luck. And about 20 years ago, a friend of mine, it's not me, asked her advisor, how do you know that you're doing a good research? And the advisor said, you actually don't. If you're lucky, you find out in 30 to 40 years. And this was before his quotes were rediscovered, so I really did find a picture of Bob Gallagher in '93. And that's what he said. Okay. Who knows who this character is? Okay. Yes. So from the Balkans, and it's good, we got someone from the Balkans to the Orient, there are these stories about this wise fool called differently, Nasruddin Hoxha and Mullah Nasruddin and Mullah and Hoxha and whatnot. And there is a story that goes that he is discussing with what they call scholar, we can call it scientist, or let him be a mathematician for this talk, whether what is important, luck or reason. And the two of them are traveling, a mathematician and Nasruddin, and Nasruddin says, I'm now really tired. I am not going to move like a meter more. So what he does, he lays down in the middle of the road, and he says, I'm going to sleep here. And the mathematician says, you must be out of your mind. It's going to be night. A truck is going to come. He will kill you. And he says, no, I'm not moving. So the mathematician says, all right, I'm going to sleep here, but out of the road, on the side of the road. So he goes on the side of the road and sleeps there, and the truck comes in the middle of the night and sees the Nasruddin, turns to the side of the road and kills the mathematician. And actually, you cannot predict other parameters, especially when people are in question. Nature may be Gaussian, but hell is other people, right? Well, I personally believe so is heaven, but that's Sartre. All right, so now this kind of concludes the entertaining part of this talk. I'll just speak a little bit longer and leave lots of time for questions. And this is, are the toughest battles yet to come? Or we know now how to do after this almost 20 years being at Bell Labs. All right. So these are quotes and hurdles. This is what was then when I started working. Actually, this first number is not from 94, it's from 1993. Who knows what this is? Christian knows, no? It's the, it's the world record for running a mile for men. And today is a little bit better. But the thing is, it took actually a long time for people to go under 4 minutes. And then once when they did it, there are quite a few records. Many people ran it under 4 minutes. It's exactly like for us, someone built something or proved something, and all of a sudden there is this avalanche of things. So then we had point to point. What do we have now? Networks, right? Okay. Then we had coding for physical layer. What do we have now? Okay, network coding beyond physical layer. Then we had hybrid ARQ. What do we have now? Raptor Q. Then we had implementation, guys. Someone was complaining the other day, one of the new hires at Qualcomm, actually. You know, there are these implementation guys, I never thought about that when I was a student. Well, I thought about them for 20 years, and I think I know how to handle them and what implementation means and how to respect what they're telling me. But there is something else which matters more now. It's actually modeling, because we are working with this higher, with more users. There is networks. There are other people who represent problems for us. And so it's the modeling which is a problem now, that I believe. So with implementation, we had hardware guys. What do we have with modeling?
Software gals.
Exactly, system girls. Exactly. So with physical layer coding, we had EB over N0. What do we have now? Now we have cost in traffic. And actually, I was going to talk, and then I decided it's too much to be on the stage. Yesterday, to give a short talk, is coding beyond physical layer beneficial? And there are so many unknowns that, you know, earlier we were able to say, all right, we introduced this much redundancy. We have to normalize our EB over N0. What else can get wrong? Well, if you make our pulses tinier to keep the same bit rate, maybe there will be some non-linearities. But that's about it. And now, beyond the physical layer, when you code, you are sending these packets which are increasing traffic throughout the network. And how do you really measure that? Everything changes, queues, and so Then we have alphabet size. What do we have now? In coding beyond physical layer. So we worried about alphabet size for complexity, fields, and so on, whether we want binary codes or higher alphabet codes. Now we have actually to worry about packetization. These days in LT, they're considering implementing this Raptor queue at the applications layer. And so how many of your actual Raptor queue symbols do you put in your transport layer? Do you put more symbols per packet or more packets per symbol? And there are things to argue about. So they're not really high mathematical problems, but if you don't resolve them, everything, you can really not claim that you are gaining anything. There we had colored noise. Then, what do we have now? Now we have fork join queues. So this is one thing that actually has been bothering me for a few months now. If you make assumptions that the noise is white or Gaussian, let's say white for your coding scheme, and it turns out to be colored, it's just at the end means that your performance are not very correctly estimated. It may be better depending on the system, they may be worse. But they're around there. However, when you start assuming various independencies in a network, then really things may not work out at all. And for example, in queues in networks, there are these Klein-Rox assumptions about independence. But now when you are looking and working with content-centric networks, what you are asking in chunk-based, you're asking for several chunks at the same time. So it's not several independent queues. It's what they called fork join queues. And actually, Bell Labs people, mathematicians worked on that in the 70s, like Leo Flato and Ed Kaufman. And what is a fork join queue? Suppose you go with your family to a grocery store and you're in a hurry, right? So you think we'll do better if your spouse goes to the milk line while you are at the bread line. And maybe you'll send your children want to buy vegetables and other fruits or maybe candy. But everyone will be buying something, joining a different queue at the same time. And that's a fork. You arrive together and then you go to different. And when all of you have to actually meet at the end because you're going with one car back home, and that's a join. And these things are actually very hard to analyze. And we need them if we want to have coding at a higher level. Then we had coding gain. What do we have now? Actually, I have put here a question mark. And the reason is that gain really depends whose gain. If you look at the story about Nasruddin, it was his gain. And there are other people in the mix that you have to consider. What's the best thing for the server to do may not be the best things for each of the users to do. So there are many actually metrics, and each one is optimized differently by completely different code, and we have some results on that. And I will try to show you actually what I mean by that. This is about transmitting over to different users over different channels, over what they call heterogeneous networks, basically meaning different types of users. And this joint work with Yao Li, who is a student at Rutgers, and Ashish Kisti, and his student Louis Tan at University of Toronto. So this is just a simple scenario. Here you have three classes of users. Class one, not class one, but one group, which has demand 60%. They happen to have a very good channel, which is a packet loss 5%, and they can code. Then you have user class 2, which demands 40%, happen to have packet loss 20%, and since it's just the phones, they cannot code. So every linear combinations that you send, they cannot recover. And then there is a user class 3, which is some high-paying users. They have 90% demand, 99. Packet loss is 40%. They don't get all the packets that the server, the base station says, and they can code. So how do you code for these people? And Yao has shown that actually if you want to do rateless codes, you have to optimize them differently. You cannot do these, what is it called, ideal soliton distribution. Maybe you should use these elastic codes, which are annuity, or something which is not Lobiša-Krolahi based for us. And it turns out that problem may have, has an information, or you can put it in an information theoretic formulation as a source coding problem, where actually this loss is some kind of distortion that you can tolerate, and the joint source and channel coding, and there is the erasure channel in between, and that's what Ashish and Luis are hoping to talk about at the ISAT. All right. So here I said that someone would like to maybe receive only 60% of the packets because he has smaller resolution, doesn't have time, or something like that. And it very much, as I said, coding gain depends on what you really want to optimize. So what your goals here are. If your goal is to make the service time the shortest, it's the one thing. If all these users, if this was homogeneous, all these people were the same one thing, and you want to minimize the serving time, this is basically like finding code which is achieving the erasure rate capacity. But if they're different, it's maybe some other code. Now, in order to minimize the time this server is spending to make all of these people happy, it may be that some people who are really asking very little, much less than this one, for example, this, how are these called, tablets, are asking 60% as opposed to these TVs, have very good channel. Why would they wait that much? And if you look from that point of view, you arrive at a completely different code also. There can be another point of view that you say, all right, you are asking, like this guy, you're asking a little, but your channel is not that good, so somehow I have to take that into account. That's another metric. So there is not only one coding gain, there are really many things that you want to optimize. Each one will give you a different code that may be a different point into some kind of array distortion region, but maybe not. If here people are looking for only 60% or for 20%, then this content has to be prepared. And we heard earlier in the week talk by Intel, this content has to be prepared so that 40% and 30% means something, not only 100%. So you don't have this cliff effect. So this is something that my postdoc Sylvia she's an NSF postdoc now at Bell Labs until July, working at Bell Labs. So she's basically looking at following and making a system which would follow the rate distortion curve as close as possible. So what we have now is when we know a certain channel, we optimize, we compress the data to match the channel capacity. If the channel becomes better, then the distortion stays the same. If the channel becomes worse, the distortion becomes maximum. So you don't want to do that. There is work at MIT. It's called softcast. This one is kind of information theoretic. So what we do, we divide actually the network resources and the channel resources into some units, and then compress the data, the source, so that it matches the small unit, and then independently compresses to matches the same unit, something like a CEO problem. And then we do some kind of a joint decoding, maybe majority logic or some chase combining if it's a Gaussian channel, and we can follow these curves better. And here we are actually departing from these curves, and then that's not a very good thing. So there are some actually patents to remove that. Okay, so again, why would that matter? Because there will be people who will operate here and people who would operate here. And people may even differ at in other aspects. And there is this entire effort, which we call video coding for customized direct access, And there are some video people at Bell Labs here. Ozgun Bursalioglu was my summer intern and student of Giuseppe Caire. She has graduated now, is with Docomo, and then Ertem Tanchel. There is some work that they did when she was his master students that is kind of applicable here that I'll mention later. But what are the diverse viewing interests? So suppose this is some kind of a game, soccer game, and any man would like to see where the ball is. So that is where he is looking. So he's not really interested in other. Any tomboy like myself would probably look at her favorite player, or someone in defense usually was for me. So you would like to actually compress this so that both of these people can access what they want. And of course you can compress this entire thing and then uncompress it at each place and they can watch it. In point to point, you compress it once and you consume it at other end. And here there are different consumptions, and someone may want to directly access a part. They also call it random access, meaning it's not sequential. When we compress, we make hashing or code. So this label, this hash is basically this parity or whatever combination is a hash, is a label, has nothing to do with, like in analog coding, with what was at the input. So there are several things that you're losing here. One is you operate over shorter lengths, and there is a penalty to pay for that if you want to compress in these smaller areas. And another is you are missing on correlation. So even if it's an uncorrelated source, just to compress it over a shorter length, you would have a penalty to pay. If it's correlated, and if it's a video, these people here in the last row, Patrice and Jean-François did some experiments. And Carl, who is actually our group manager now, assumed that it's just Gaussian source. We were happy about that. Gaussian source with some kind of a topics cross-correlation matrix, and make a smaller blocks as opposed to larger, and showed the same trends as they were observing when they're partitioning this to compress. Okay. A related problem, also kind of direct random access, is the following. So do you miss this guy? That's the only thing I miss from the previous location, actually. That was the bear in So you have here two cameras. One is bluish, it's grayish here, and the other is pinkish. And they somehow overlap at part of a body of the bear. And there is a head, which is only seen by X, and legs here in the back, which is only seen by Y. And you may want to, and these cameras are not communicating. And so it's a distributed compression problem. And they are trying to compress, but in a way that if you look only at the X, and the problem is that you don't know what the user would choose. If he looks only at the S, he wants a certain distortion. If he looks only at the Y, he wants a certain distortion. And if he looks to decode both, he wants, say, zero distortion to make a problem easier. So there is some kind of a multiple description flavor here, but it's not multiple description because you're not describing the entire source. You're describing a part of the source and another part. Another thing to think about is you may want to know a temperature in San Diego and temperature outside at UCLA, but they may differ in 1 bit. So if you say 1, you can just say for 1 degree, you can say just whether it's minus or plus, so that it's 1 bit, this Leppian wolf in action. However, if you receive only that 1 bit, then you really don't know what the temperature. You just receive this bin index, which becomes meaningful when you have side information. So how do you make this graceful? So what if the switch changes according to some random pattern? And Ertem and Ozgun were working on these things, and I'm trying to formulate it in some kind of general terms, not completely only information theoretic, and is that if you compress this joint source, this entire bear, I call it X sin and Y, into L symbols, then there is some minimum L star required for a joint recovery of X and Y. This is determined by the entropy of the source, say if it's discrete memoryless. There is some minimum Lx or Ly star that is required for a perfect recovery of X, right? That's, again, entropy is, If you make a perfect recovery of X and perfect recovery of Y, this number of bits together is larger because of the correlation than what you need to just compress X and Y jointly. And based on, if it's a memory source, just on entropy subadditivity. So we can perfectly reconstruct with L star either X and Y if we apply Slepian-Wolf, but that's not what we want to do. We want to ensure certain distortion. Okay? So what if we want to guarantee certain reconstruction fidelity of X and Y? So this type of problems. And this is actually to a little bit tell it in a different way, which I'm not going to bother you about at that time. So we heard at the previous talk that source coding is not popular. Actually, it's kind of strange. With all this data that we have in video, don't you need someone to compress it? I've been trying to tell that to my management for years now. Something may happen, I hope. So Raymond was advertising yesterday positions at his universities, but if that doesn't work, you may want to try Bell Labs. Here, what we want is jack of all trades to complete 80% of half of the list of some of the jobs that need repair. And actually, we have a dismal hiring record. It's in the late 90s, Emre and Rudy left, and then we got, soon after that, Gerhard and Alexa, and then Gerhard left, and we got Urs, and that's it. Many other people left, were not replaced. And since this is about application, this is Giancarlo Rota, who wrote Indiscrete Thoughts in 1996. Died just 3 years before he died. This picture was taken in the 71, just before he turned 40. And he says that one of the rarest mathematical talents is the talent for applied mathematics, for picking out of a maze of experimental data the 2 or 3 parameters that are relevant and to discard the rest. And then he says again, this talent is rare and it's taught only at the shop level. And with this, I would like to conclude.
So are there questions for Emina? It was a wonderful talk. How long did it take you to prepare that?
Do you know the story of?
Years and years. No, I don't know the story.
So Alon called me up last Tuesday. I didn't want to advertise that. So that's why you had the abstract of my short talk already sitting there. It's years of experience. The last slides, of course, I had the more technical slides. I have given a TPFL with the Eiffel Tower instead of the bear, so those were cheating. But for the rest, they're all new.
Any other comments or questions? If not, let's thank book.
Yeah, I will add a comment. Recently, I attended the talk of Sir Richard Hunt, who was a Nobel laureate in medicine in 2001. And in the line what he said about Danny Kahneman, who was another Nobel laureate, he said, you know what, when I got the Nobel Prize, my wife told me, if you can get it, anyone can get it.
That probably applies to me. Like, speaking of this title and the spouses, so Alon called me a Tuesday last week and had abstract and title review later that evening. So I came late from work and I said, show this title to my husband. He said, oh, it's horrible. So I had to come up with what you have now. So it's good that he intervened. Henry?
So in the last couple of problems you described,
Uh-huh.
you guys have partial results?
Yes, there are bounds which we believe we can match them, achieve upper and lower, let's say, for the audience. And Erta may be suspicious. Ozgun is optimistic. And right now we're a little bit working on some other problems. This may be one of the possibilities for summer jobs, maybe some other. We had a recent reorganization that, so we don't know yet, for example, what. But no, we have not solved these problems. So and do have partial results.
Anything else? If not, I will leave you with a request that comes from Emina and myself and Bonnie. We were very reluctant to tell anyone that story about the tax